Hello, good morning students. Welcome back to chemistry online classes. Okay, the last lecture 7 students I completed a very important thing, that is what? Calculation of thermal charge of an atom and also bond parameters like bond lengths, okay, bond angle, then what we call it as bond order and bond dissociation energy, right? This bond order is directly proportional to bond strength, bond length, okay, inversely proportional to bond length but directly proportional to bond dissociation energy. That what we have discussed in the last previous lecture, it is lecture number 7. So today we are going to study another important concept in chemical bonding, that is called dipole moment. See, this dipole moment is one of the important concepts. By studying this dipole moment, students will come to know whether the given covalent molecule, whether the given unknown, that is molecule, or a covalent compound or covalent molecule is polar or non-polar. That will come to know by using this concept of dipole moment. Right? So let us study what is the dipole moment, what is its SI unit, and how it helps in determining or deciding whether the given molecule is carrying the charge, positive charge or negative charge. That is called polarity. Okay? Right. Now, see here, what is dipole moment? This is one of the important concepts. It's a properties of a molecule by which we can decide polarity of covalent compounds. What is actually it is? If you consider a polar molecule, suppose for example, if you consider a polar molecule. First of all, polar molecule means it is containing both positive end and negative end. Both positive end and negative end. Let us assume here a positive end and one negative end. Okay, Q plus, right? And Q minus. Now distance, if they are separated by a certain distance, that is d. Okay, now what is dipole moment? Dipole moment is just nothing but it is the product of definition. What is the definition? It is defined as the product of magnitude of charge and distance between the positive and negative end of a molecule. Okay. What is dipole moment? It is defined as a product of magnitude of the charge and distance between the positive and negative end of a molecule. That is called dipole moment. And this dipole moment, very importantly, it is a vector quantity. It is a vector quantity. Very important. That means it depends on both magnitude as well as direction. It is a vector quantity. Right. Now, mathematically, this dipole moment is given as symbolically as mu. Is nothing but E into D, or you can also write it mathematically. Mu is equal to Q into D, or Q into that is a R. Both are right. Where see E or Q stands for magnitude of charge, right? And D or R stands for distance, the separated distance between positive and negative end, right? So this is called dipole moment. What is this electric charge? Electric charge you already know. Its value is absolute value is, and from the atomic structure knowledge, 1.602 into 10 raised to minus 19 coulomb, and distance between these positive and negative end. If you multiply, you will get mu. What is this mu? Dipole moment. Okay. Right. Then what is the SI unit? SI unit of this SI unit of this dipole moment is very important. SI unit of dipole moment. Dipole moment is that is d bar. D bar, that is capital D. 1 d bar is equal to 3.3564 into 10 raised to minus 30 coulomb into meter. Okay, coulomb into meter. See, coulomb is the SI unit of the charge and meter is the SI unit of the distance. That's why coulomb into meter. This is very important. Value of 1 d bar is 3.3564 into 10 raised to minus 30 coulomb into meter or 10 raised to minus 80 ESU, electrostatic unit, that is in CGS system and this is in the SI system. Very important. VVIMP, very important for 1 marks theory, even for CET also. Right? So this is the basic idea of definition of dipole moment. What is dipole moment? It is defined as the product of magnitude of charge and distance between the positive and negative end of the molecule. It is a vector quantity. It depends on both magnitude and direction. Therefore, mathematically it is given by mu is equal to E into D or Q into R, where E is the electric charge and the D is the distance separated between the positive and negative end of molecule. Or here also Q stands for charge and R for distance. Therefore, it is expressed in SI unit as 1 d by. So 1 d by nothing but its value is 3.354 into 10 raised to minus 30 coulomb into meters. That's it. Now I will tell you how it will help us in determining the polarity of a molecule. Remember, okay? Right. This is the first definition and information. Now let us will apply this application of this dipole moment. It is used to determine polarity of an unknown molecule. How? Let us see the examples. Application of dipole moment in determining the polarity of a molecule. Remember students, point to be noted. Please note the point. If mu value is 0, that is considered as non-polar. If mu value is not equal to 0, then it is a polar molecule. Whatever small in between 0.1, 0.2, that is considered as polar molecule. If it is not exactly equal to 0, then we consider a given molecule as non-polar. But how to decide? So that's only by using formula mu is equal to what I told you, E into D. How it is determines a distance once again in terms of bond length. That's why I told you yesterday itself. How it is done, sir? Experimentally by spectroscopic method. Remember, they will provide you and you have to multiply 1.602 into 10 raised to minus 90 coulomb, that is absolute charge, and that distance, bond length, will give you mu. Okay? If this comes down to 0, then it is non-polar. It comes out to be some value, then it is polar. Okay? Let us I will show you with some examples. For this, you should have the knowledge, the basic strong knowledge of periodicity, especially electronegativity. Okay? Which is more electronegative, which is less electronegative. That will help you very much in deciding your polarity. Okay? And also bond movements. Let us see one by one. The first basic example what you can take is, if you are given hydrogen fluoride HF, whether it is polar or non-polar, how do you decide this? Hydrogen fluoride HF. Okay, see here. Hydrogen and fluorine, you know that they are under one single covalent bond, right? Okay. Out of this hydrogen and fluorine, which is more electronegative? Fluorine is the most electronegative element of the periodic table that you know. Hydrogen is less, right? So remember students, this order I have to remember. decreasing order of electronegativity which are being given in calculating formal charges also. Once again I will repeat: chlorine most electronegative, followed by oxygen, then chlorine, then bromine, then iodine, then nitrogen. After nitrogen, it's a turn of carbon. After carbon, boron. Okay, beryllium, lithium, right? Helium, lastly hydrogen. Please remember this decreasing order from your periodicity of elements. With the help of this, now I will tell you one by one. Okay, right. Hydrogen the least electronegative, fluorine the most electronegative. So, see, it will show how the direct activity depends on both magnitude as well as direction. Therefore, generally, see, it is shown by the arrow mark. Dipole moment inside electron to get shown by the arrow mark. Okay, that is it. Now, fluorine is more electronegative, therefore, bond here movement inside of the show from hydrogen towards fluorine. Getting delta minus, and this is delta plus. Okay, so like this here, see, charge is separated, and mu value upon multiplying this E into D or Q into R, it comes to be around 1.96 D by D. So how do you get this value? Multiplying charge 1.60 to 10 raised to minus 19 coulombs, and distance between this H and F, that will be given experimentally. Bond length multiplied by bond length will give you this one. 1.96 D by unit. See, mu is not equal to 0. Then what is your inference? It is highly polar. Remember, HF is highly polar. Highly polar in the nature. Like this, you have to go on deciding one by one. Okay, that is the first example. Hydrogen fluoride. After hydrogen fluoride, if you come to next, in case of polyatomic molecule, net dipole moment is given by the vector sum of dipole moments of various atoms. That means this is simple molecule, diatomic molecule, heteronuclear diatomic molecule. But in polyatomic molecule, it is a given vector sum addition. Let us see what is that. This is one example. Okay, then coming to next, second example, that is H2O water. Okay, now you already know water has a band V-shaped structure, hydrogen. Now you only have to compare electronegativity. No lone pair of electron not needed. If you still want, you can write it. Lone pair, right? Okay. Out of oxygen and hydrogen, which is more electronegative? Now you tell me here. Oxygen is more electronegative than hydrogen. Therefore, write all moments from oxygen to hydrogen to oxygen, and this is delta minus, not delta 2 minus, only delta minus. That's it. Right. So net dipole moment here does not cancel. So in polyatomic molecules, okay, dipole moment is vector sum of, okay, it is a vector sum of, in polyatomic molecule it is a vector sum, or just we can also write it as the vector quantity and density. Vector sum of dipole moments. Vector sum of dipole moments. Remember. Okay. So this I will do. That's only that knowledge issue. Less electronegative will give to more electronegative. Will attract the modern pair of electron towards this. Therefore, delta minus one which donates delta plus delta minus. Because net dipole moment is cancel each other and mu net dipole moment will be 0. If they are on the same side, remember mu is not equal to 0. This is also not to be noted. Okay? Hence it increases on oxygen atom. It is also highly polar. Whatever is highly polar, the mu value after multiplying E into D, what you will get? 1.84 D by S. It is also highly polar. Highly polar in nature. After HF, water is the next polar molecule. Remember. Like I said, to go on one by one, solving this, deciding polarity of water. Very, very important for CP especially. Okay. Now coming to next another one. After water, let us go for next another very important example. Generally we will came across, that is beryllium fluoride and boron trifluoride, and even ammonia also. Right? Okay. This I will wind it up once again a little bit. See, less electronegative. This is more electronegative. Less electronegative carries positive, more electronegative negative. Okay? And this is the bond. See, significance of which side electron is going. That is shown by dipole moment. If the dipole moment directions are like this, okay, if they are the opposite side, they cancel each other. Right? If they are the same side, they does not cancel each other. Right? Okay. So let us see with the example. That will come to know very clear. Okay. This is one example. Now let us move on to another important third example in this particular example. After water, now if we come to beryllium fluoride, BeF2, beryllium fluoride. According to your Hilbert formula, it is linear molecule BeF2, that you already know, right? See, beryllium sinks, it is here. Fluorine bond electronegative. Therefore, bond moments need to show like towards fluorine. Now you see, these bond moments are opposite to each other. That's why I told you. Bond moments are opposite to each other. Then, generally, if they are opposite to each other, then they cancel each. Right? That means here net dipole moment on beryllium atom is what? 0. Therefore, mu is 0. Mu is 0 and it is polar. But it's a linear molecule. And water was bent-shaped structure. Bent V-shaped structure. Right? Okay. Now coming to next third example. After beryllium fluoride, now boron trifluoride, BeF3. Very, very important for C. Let us see. Boron trifluoride. See, here it can be written as like this. Here. And how do you come to know how to write like this only? That's why like start formula I told you, right? Okay. Now boron each containing one share with the fluorine atom, right? Now fluorine is more electronegative than boron. Once again comparing. Fluorine more electronegative than boron. And for bond moment towards fluorine, this is very, very important. Bond moment towards fluorine, bond movements towards fluorine. Now you see this, both they are in the opposite direction, they cancel each other. Even here also, here, third side is equal to the fourth side. The resultant bond moments of the third side is equivalent to fourth side. This is one of the rule in vector addition, that is in mathematics. Right? So net dipole moment of the boron, okay, will be once again what? Mu is equal to 0. It is also, non-polar. Extremely sorry, it is non-polar. And here also it is non-polar. Non-polar in the nature. Like this, we have to decide based upon the electronegativity. See here. So this is having the trigonal planar structure that will come to explain the valence bond theory and VSEPR theory. That means this dipole moment indirectly not only decides polarity, even it helps it to some extent to know the shape of the molecule, okay, or geometry of the molecule. See, linear, triangular, planar, boron, trifluoride. I will once again I will repeat. See here. These two sides are opposite like this. You have to imagine like this. And this side there is only one, therefore third side is equal to the fourth. You have to imagine in three-dimensional way. So resultant third, that means two sides are equal to the third side, therefore it is mu is 0. On the boron electron density, because it is giving away all its electron. What is electronegativity? Capacity of atom to attract bonded pair of electron towards itself. Electrons को अपनी तरफ खींचना, खींचिंग effect बोलते हैं इसको, खींचिंग effect. Okay, fluorine is having more खींचिंग effect than boron. Remember, okay, boron will lose, fluorine will gain. Therefore, delta minus, right? Delta minus, boron delta plus. Got it? Not 3 plus, only plus. That's it. Okay, this now we can decide polarity by using this dipole moment. Not only polarity, but we will come to know geometry and shape of the molecule. Okay. After beryllium fluoride, boron trifluoride, now let us put another more examples. You come to know one by one. You have to practice this. Without practice, you don't understand anything here. Okay. That is very importantly ammonia. NH3. Let us go for NH3, ammonia. See here. Ammonia is having structure that will share out of 5 electrons 3 hydrogen with the 3 electrons with 3 hydrogen and 1 lone pair. This is it. 1 lone. Okay. Like this, if you take another example, here we have 3 nitrogen trifluoride. It is also same thing. Nitrogen trifluoride NF3. Compare those. Instead of hydrogen, now it is fluorine, and 1 lone pair. Okay. Which is a more, that is a polar in nature. Higher the mu value, more the polarity in the nature. Remember. That means hydrogen fluoride is having 1.96 d by unit, whereas water 1.84 d by. But ammonia 1. Now I will tell you 49, and this will be less. Let us see 1 by 1. The central atom is nitrogen C. Okay, now hydrogen is less electronegative, therefore electron will move towards what? Nitrogen. Therefore bond moment is on the same side. Even electron pair is present. But here NF3 not like this. Fluorine is most electronegative. It will attract the bonded pair of electrons towards itself. It is away from the nitrogen. Only we having lone pair of electron nitrogen atom. Only we having this. This is responsible for what? That is. But this is not answer. That is responsible for polarity. Now ammonia. This ammonia is having mu value, that is 4.96. That means mu value for ammonia 4.96 d by unit. Sorry. I will just refer and tell you. Okay. For ammonia it is mu value of the multiplying E into D 1.49 or 47 d by unit, but this will be mu value 0.27 d by units. Why so? After multiplying E into D 0.27 d by unit. So what is happening? Why it is less here and why it is more? That depends upon what? Atom. Atom surrounding the central atom. Okay. See, hydrogen is less electronegative, but whereas fluorine is more electronegative. Makes sense? See, give the attaching atoms, surrounding atoms are less electronegative. They will give the electrons to the nitrogen. That's why mu value will be more. Means as the electronegativity of surrounding atom decreases, dipole moment increases. But if the surrounding atom are more electronegative, then dipole moment decreases. But both are what? Polar. Polar. This is also polar. But ammonia is more polar than nitrogen trifluoride. See, this is a very, very important question in the theory. Already so many times asked. Why ammonia is more polar than nitrogen trifluoride? Give a reason. You have to compulsorily if it is asked for 2 to 3 marks, you have to show this bond movements. And what is the reason you will write here? In ammonia, the bond movements are on the same side. They does not cancel each other. Whereas in nitrogen trifluoride, bond movements are on the opposite side. Okay, opposite side. Therefore, net dipole moment here decreases. By the net dipole moment on the nitrogen here it increases. That's why net dipole moment increases here and here it decreases. But both are having what? Both are having pyramidal structure. Pyramidal structure. Remember, pyramidal. Both are having trigonal pyramidal structure or just only pyramidal structure. Due to that bond. Actually, it should be tetrahedral sp3 hybridization, but no, they are pyramidal. What is this hybridization? That I will tell you the next part of this dipole moment and valence bond thing, because they are interrelated to one another. So this chapter is we are having so many concepts, so don't confuse, please. Okay. Therefore, we are going step by step, simple to complex examples. Right? I'll repeat once again here. Hydrogen less electronegative, therefore now I will write delta plus nitrogen delta minus. And here fluorine more electronegative, delta minus and nitrogen here delta plus. This is the important point to be noted. That's why at the beginning I have not written. Otherwise you will get confused. Right? If less electronegative towards the atom, more electronegative away from the atom. That's why I told you it depends on both magnitude and direction. Okay? Right. See here the bond moments you tell. So this is opposite side now. This is also opposite side, not like that. It is lone pair of electron. If there is a lone pair of electron, definitely it will have some dipole moment. It will not cancel with this direction. Remember, each point to be noted. If there was no any lone pair, then definitely it will become non-polar. Mu value becomes 0 and non-polar. But due to this lone pair, see very small value, 0.27. Whereas here it is high value because of this 3. 1.49 or 1.47 d by ds. Okay. So that's about 5 examples. So what I explained now, HF, okay, then H2O, bent V shape, HF, linear, and then water, bent V shape. Right now, taking example of ammonia and NF3, you will come to know very clearly. And I think now you are getting the grip and idea how to decide polarity when unknown molecule is given. For that, you should have to compulsorily perfect with Lewis dot formula. See, yelli vattu sangaya, matta allige vattu sangaya. Right? So, please students, मैं आपको वही बता रहा हूँ, आप लेविस डॉट फॉर्मूला और परमाणु चार्ज परफेक्ट करना नहीं तो ये डाइपोल मोमेंट में कुछ भी नहीं समझेगा. Got it? Right. Now, without wasting time, let us go for another more examples. Not only this, there are some other molecules. which are helpful for your CE purpose. Let us see. If you are given CO, carbon dioxide. Structure of carbon dioxide is like C double bond O, C double bond O. See, Lewis dot formula we have studied this. Okay. Now carbon is less electronegative, oxygen is more electronegative. Therefore bond, making it delta minus. Carbon delta plus. See, bond moments are opposite side. mu value 0. So what it is? Non-polar. Very simple. But it is having what? Linear shape. Okay? This is carbon dioxide. Likewise, carbon disulfide also, CH2. Very good example. CH2 is an organic liquid. This is the liquid form. Carbon here also surrounded by CH2. Okay? It is also expanded again, no? 2468, 2468. But carbon only. Carbon disulfide. Here also same thing. Sulfur, carbon, more electronegative. So, like this is also linear shape, the value will be 0. Sorry, but sulfur, down the loop generally electronegativity decreases, but across the current it increases. That's why I show it is also non-polar. Okay, now coming to after carbon dioxide, let us go for another example. Some symmetry of the molecule like methane, CH4. See, CH4 we can write like this. Methane. See, carbon is more electronegative than hydrogen. So bond moments towards carbon, towards carbon, towards carbon, towards carbon. Right? Delta plus, delta plus, delta plus, delta plus. And this is only delta minus. Okay, delta minus. See now what about whether this methane is polar or non-polar with them? See whether they are on the same side, bond moments are on the same, whether they cancel each other? No. Here also, exceptional case, very very important. Mu is 0. Why? Due to symmetric. Due to symmetry. That means this molecule can be cut into equal parts. That's why due to symmetry, mu value 0. Non-polar. Very very important for CET. How side is cut into equal C here? Yes, you can make CH4. अगर आप इस मॉलिक्यूल में देखो, ऐसे कट किया on any side if you cut it will cut into two equal parts CHC. Then it is contained in plane of symmetry. Right? These are exceptional molecules. Very important for CET. But the same thing. When you take another one, very important is CCl4, carbon tetrachloride, CCl4, carbon tetrachloride, Cl. Instead of hydrogen of this time, chlorine. Okay. Now you know that chlorine is more electronegative, right? The bond went toward this side, and this side, and this side, right? Delta minus. This is the delta plus. So opposite side cancel. Now this is definitely 0. This is also non-polar. Okay. Why methane is non-polar? Due to symmetry, not due to bond moments. These are exceptional cases. Like this, if we go for hydrocarbons, that is methane and carbon tetrachloride CCl4. Both are non-polar. This is due to symmetry and that is due to more electronegative on central atom. Right? Okay. Now after this, sometimes they may give you very importantly some more examples. Students, I want to discuss with you. In organic chemistry you don't know, that's why I am not going for those examples. When you come to know organic chemistry, then you apply this and use for those examples. But still, some more examples I want to tell you. Xenon dichloride and xenon tetrachloride, whether they are polar or not. Let us see. Xenon dichloride, xenon is having 8 elements. It is a noble gas. Out of 8 elements, it will share Okay, 2 electrons with the 2 fluorine atoms. Right, the remaining it will have 2, 4 and 6. That's a lone pair. This is the structure of xenon difluoride. Okay, whether it is polar or non-polar, that's important. See, fluorine more electronegative, therefore here bond mates cancel, but what about the 2 to lone pair? Mu value is not, because lone pair of proton, this is non-polar moment. Okay, non-polar moment. Why? Due to 3 lone, or else it can also be written as like this also. Fluorine, right? sp3d hybridization. sp3d hybridization is a bent shape like bent T-shaped structure. It's T-shaped structure. Okay, just if you remove this. Okay, right. sp3d hybridization 120 degree, 3 axial to equatorial, but it is non-polar. Okay, but due to this lone pair, this can also be written as linear. Distorted geometry is linear, but actually it should be trigonal pyramidal. According to sp3d hybridization. Okay, now HCl4, xenon difluoride. See, it will share them 1, 2, 3, 4. Fluorine. Remaining 4 as a reference. Fluorine more electronegative. Fluorine more electronegative. Fluorine more electronegative. See, like this, they cancel each other, opposite side. Even this also. Even though lone pair of electrons are present, they cancel each other because equal are present. So here this is mu is 0. This is polar, and this is non-polar. Like this, some exceptional examples are very important for CET purpose. Okay, these are compounds of xenon. Like this, you can go for so many examples. If and if, please note this one. You have to know very perfectly. Fluorine is the most electronegative, then second highest one is oxygen, followed by halogen, chlorine, bromine, iodine, then nitrogen, carbon, boron, beryllium, lithium, helium, hydrogen. Least electronegative and also less electropositive is hydrogen. Most electronegative, fluorine. Okay? Right. That's about very important example just I discussed with you. Now, still more some examples like for example, if you are given some compounds like HCl, okay, HBr, even HI, just now they are given H. These are called PV type of molecules, heteronuclear molecules. Okay, bond metals here, delta minus, delta plus, delta plus, delta plus, delta plus, delta minus, delta plus, delta minus. See, all are polar in nature because of electronegativity, right? But check, as electronegativity of the atom increases, halogen increases, mu value dipole moment increases. Therefore, HF is highly polar than HCl, HBr, HI. Remember, the order is like this: HF, HCl, HBr, and HI. This is decreasing order of polarity. Which is highly polar? Beryllium fluoride is highly. Okay, right. Next, another example of this is wavy type. Just I give you some example now only. CO2 or you know now. H2S, this is also you know, and H2O is also you know. This is C double bond O, linear, non-polar, linear. Okay. Now this is yes. Hydrogen, which is more electronegative. This is therefore this is mu value is not equal to 0. No, this is polar. H2O. This also like this. Generally bond moment here it increases. So mu value not equal to 0. No need to remember that value. That's why just not equal to 0, right? And just write it as polar. Okay. This is angular or band. This is also angular or band. This types of molecular what? AB2 type. Okay, AB2. The center atom is here A and this is B. Got it? And after this AB2 type, now we have done NH3, NF3 also given and BF3. You already studied it. NH3, NF3, BF3. Right? This is polar. Already you know. This is also polar. Already you know. And this is non-polar. Third side. Okay. This is AB3 kind. Pyramidal, and this is trigonal link. AB3 kind. AB3. Right? And just now I given you the AB4 examples like ethane, CH4 and CCN. Non-polar due to symmetry and this is due to bond moments. Non-polar. Right? Like this are having tetrahedral structure. Tetrahedral. Like this, by studying these various examples, dipole moment help us in determining what polarity of molecule, whether given unknown molecule is polar or non-polar. If mu value is 0, non-polar. At least to point something any decimal, also it is polar but less. Remember, but it is polar. Right. That's about information regarding dipole moment. See, there are so many examples are there. Organic examples are there. Organic chemistry will come to know because organic chemistry are not studied. That's why I will not go through those examples. Right? Okay, this is more than enough to understand what dipole moment. That means see, it is one of the physical quantity we can tell, with the help of which we can decide polarity of unknown molecule in chemistry. It is a vector quantity. It is a product of magnitude of electric charge and distance between the oppositely charged end of polar molecule. That is called dipole moment, and it is expressed in d by unit. 1 d by unit is 3.3564 into 10 raised to minus 30 coulomb into meter. C, capital C, coulomb, and small m, that is meter. Okay, charge into distance. Charge, coulomb, distance, meter. Remember. Okay. See how they will ask this question. They will give you these molecules, classify them into polar and non-polar. For that purpose, you should have to practice this. Compulsory one question in theory. Okay. CET also very important. Some unique character only them. For example, methane I told you, CCl4, right? Ammonia, NH3, NF3. Very important for CET purpose. Right. Now this dipole moment, I will take you to next another important concept, which is very, very important for your theory purpose. We are entering into now valence bond theory. What is this valence bond theory? VBT. Valence bond theory. See, in valence bond theory, you will come to know very clearly orbital overlap formation of covalent bond. Until now, we only know covalent bond is a bond which is formed by mutual sharing of electrons between the combining atoms, whether of same or difference in electronegativity. Okay, now I will tell you what is this polar covalent bond and what is non-polar covalent bond, because now you come to know dipole moment. Okay. Now here in this, before going to valence bond theory, what is the polar covalent bond and non-polar covalent bond? Polar covalent bond is the covalent bond present between two different atoms. Two different atoms. Okay, two different atoms are where bonding pair of electrons are shifted towards more electronegative atoms, more electronegative atom. Remember, such type of bonds are called as polar covalent bonds. Now we are studying, for example, just example HF, hydrogen fluoride, then HCl, hydrogen chloride, HBr, hydrogen bromide, HI, that is hydrogen iodide, H delta plus H delta minus, H delta plus delta minus, H delta plus Br delta minus, H delta plus and I delta minus. Remember, polarity wise difference in electronegativity. One less electronegative, another one more electronegative. Okay, this is polar covalent bond. Okay, right. Now coming to next, what is non-polar covalent bond? Non-polar covalent bond is a bond in which if the bonding pair of electron or shared pair of electron is concentrated at the center of atom, then it is called non-polar covalent bond. Okay, this is an example for heteronuclear molecules. What is non-polar covalent bond? Non-polar covalent bond. Non-polar covalent bond. Okay. What is this non-polar covalent? This is polar covalent bond. Sorry, now it is non-polar covalent bond. The covalent bond present between two similar atoms, not different, two similar atoms in which bonding pair of electron is concentrated at the center of atom, and is called non-polar covalent. For example, see, just I will give you here only because both are related to each other. Homonuclear diatomic molecules like hydrogen. See, it is concentrated at the center of two atoms. Hydrogen, okay, then chlorine, oxygen, right, then nitrogen. Generally, what will write here? H2, F2, O2, N2, N1, Cl2, Br2, and that means this does not carry charge. Non-polar does not carry charge. Polar carrying partial positive, partial negative. Why? Due to difference in electronegativity of the atom. One more electronegative carries negative charge, less electronegative positive charge. Here, see, same electronegative. Why? Because same atoms. Only bond order different. Single, double, triple. Cl2, Br2, and C. Okay? This is how, by the concept of Dipole moment, will come to know what is polar covalent bond and what is non-polar covalent bond. Okay? Right. We'll just right, students. See, now we have come to know with the help of dipole moment we can determine or we can decide the polarity of a molecule. And also I given a definition of polar covalent bond and non-polar covalent bond. Okay. Now we are going to study very important theory that is called as valence bond theory, where you come to know very importantly the orbital overlap concept. Orbital overlap concept of formation of covalent bond. The question arises, why there is the need of this theory? See, you have studied Lewis dot structure given by G. N. Lewis and Coherent. With the help of Lewis dot structure, one can write only structure of molecules, but it doesn't give any idea about chemical bond formation and also bond dissociation energy associated with the molecule. The bond dissociation energy of hydrogen is 438 kilojoules per mole, whereas for fluorine it is 158 kilojoules per mole. Why it is more for hydrogen and less for fluorine? This reason is unable to given by the G. N. Lewis and Coherent. That is Lewis dot structure, and also there does not speak anything about shape of molecule or geometry of the molecule. Even another theory is there, VSEPR theory, valence shell electron pair repulsion theory. That theory also explains the formation of molecule without hybridization. It tells you only about geometry, but does not tell us about shape of molecule. I'll tell you further while explaining this, especially VSEPR theory, what is the difference between geometry and shape. Now, remember, to overcome these limitations, what are the limitations? Does not tell us about chemical bond formation, regarding bond dissociation energy and shape of the molecule. We are unable to get this information from what? This Lewis dot structure as well as valence shell electron pair repulsion theory. To overcome these limitations, in the year 1927, Hitler and London. Okay, Hitler and London. That is same name, that is London, scientist name, Hitler and London. They put forward this valence bond theory to explain the formation of covalent bond even through orbital overlap picture. Later it was modified by Slater and Pauling. Okay, Slater and Pauling. Later it was modified by Slater and Pauling. Let us see what are the postulates of this valence bond theory and how it helps us in giving idea about formation of this covalent bond. See, according to this valence bond theory, how covalent bond is formed? First one, the first postulate of this valence bond theory, very very important for theory 2 or 3 marks. What are the postulates? First postulate is number 1, covalent bond is formed from overlapping of two atomic orbitals of nearly same energy and proper symmetry. And secondly, the combining atoms, the combining atomic orbitals. Okay, the combining atomic orbitals should be, this is very important, should be half-filled, containing electrons with opposite spin. Okay, half-filled containing the electrons with opposite spin. And when covalent bond is formed, they lose energy and become stable. That is stability. When covalent bond is formed, the molecule becomes stable. becomes stable. How? By losing energy. Lower the energy, higher the stability. Then fourth one, higher the extent of overlapping, stronger the bond. Higher the extent of overlapping, higher the extent of overlapping, stronger the bond. Stronger the here extent of overlapping, stronger the bond. Extent of overlapping. Extent of overlapping follows very importantly. That is follows the order SS, SP, less than P and P4. It's very important for 2 to 3 marks in the theory. Remember, how covalent bond is formed? It is formed by overlapping of definitely 2 atomic orbitals, and those 2 atomic orbitals, they should be half filled with containing electrons with opposite spins. Okay, that means they should compulsory half filled like this, according to Hooke's rule. Then definitely they are overlapped another opposite spin like this. Okay. Then when covalent bond is formed by overlapping like this, they lose energy and become stable. But higher the extent of overlapping, stronger the bond, which is very important. How much the extent of probability of overlapping takes place, that much stability increases, strength increases. The extent of overlapping follows SS, SP and P and P. That means there are 3 types of overlappings. Especially, once again there are 2 types depending upon this orbital overlap. How covalent bond is formed, in which fashion covalent bond is formed, there are 2 types of covalent bonds. One is called sigma bond, another is called pi bond. Now let us, I will give you what are these sigma bonds and what are these pi bonds and the differences, and also I will explain in detail what is this SS, SP and PP, sigma overlapping, and P pi overlapping with the differences. Okay, right. Let us, I will tell you. Very importantly, what is sigma bond and what is a pi bond? First one, sigma bond. Symbolically we will write like this. There are 2 types of overlapping. That means this bond which is formed, there are 2 types of overlapping. One is called axial or head-on overlapping, that is called sigma bond. Sideways or lateral overlapping, that is a pi bond. Okay. Notice sigma bond. The covalent bond which is formed by overlapping of 2 atomic orbitals. 2 atomic orbitals along the internuclear axis. Very important. Internuclear axis or head-on overlap. Head-on overlapping. It's called, what it is? Sigma bond or sigma covalent bond. Okay? Right. Along the internuclear axis, that means the 3-dimensional region will have Px, Py, Pz like that. I'll tell you one by one. There are actually 3 types. First one, S overlapping. One S atomic orbital, another SS overlapping. SS overlapping means consider formation of hydrogen. S orbitals are spherical in shape, that you know. This is one S, this is another S orbital. Let us take for hydrogen. Okay. Both are having unpaired electron. Unpaired. This is the nucleus of 2 hydrogen atoms. Along internuclear internuclear axis like this. Okay, this is called internuclear axis. Leads to formation of what? A single bond. This is sigma. SS over here. Okay. H2. This is called internuclear axis. Head-on overlap. SS overlap. Okay. Now, coming to next. SP overlap. SP overlap. Second one. SP overlap. Consider formation of HF. Very important. This is for hydrogen, right? See here they will mix up like this. Now O1, right? This is orbital overlap picture. P orbitals in fluorine C. Fluorine atomic number 9. 1 half end. Hydrogen 1, fluorine 9. 1s2, 2s2, 2p5, right? In 2p5 you are observing there are 3, 2px1, 2py1, 2p11, 2px2, 2py1. This is the last one, 2pz. Okay? It is along the internuclear axis. Let us take it as a fluorine molecule. Okay? This is of okay. How will it overlap? Along internuclear axis, like this. Along the internuclear axis. Like this, they will share. Okay? Certain generation gets paired up. H sigma SP overlap. That's it. Right? SS and SP. These are the practice students, very important. This is called internuclear axis or head-on overlap. Okay? And lastly, coming to very important, P and T overlapping. P and T overlapping. PP overlapping. PP overlapping. And P and T overlapping. P and P overlapping. See, one fluorine atom. If you consider fluorine, that is both are having this is for P and P orbital of fluorine. Okay, once again having in PZ, fluorine, PZ, they will overlap. And on minus. Okay, that leads to this is what? P and P overlapping. Okay, here and PP overlapping sigma bond. So like this, there are 3 types of sigma covalent bonds. What are those? SS, SP and P. For SS, hydrogen molecule. For SP, hydrogen fluoride molecule, and for P and P, it is a fluorine and fluorine. That means 1s atomic orbitals of hydrogen will overlap with 2pz orbital lastly. I told you condition, half filled only, not completely filled. 2pz of the fluorine atom and 1s atomic they overlap along the internuclear axis and form SP sigma overlapping. Like this, 2pz of the 2 fluorine atom, they overlap along internuclear axis or head-on overlapping and form P and P sigma overlapping. It is only along internuclear axis. Here symmetry is very important. I am repeating, students. Okay, internuclear axis only. Okay, right. If it is on perpendicular, no. is a pi bond. Remember, S and S, SP and P overlapping. And remember, always sigma bond is stronger than pi bond. Why? Because probability of formation of sigma bond is more. It is 75%. Further, we will come to know why it is 75%. That's why sigma bond is stronger than pi bond. Always sigma bond is present in saturated compounds, single bonds. Okay, even not it can exist alone, not along with the pi bond. This is about sigma bond. What is sigma bond, students? The covalent bond which is formed by overlapping of two atomic orbitals along the internuclear axis or head-on overlapping. There are three types of orbital overlaps: SS, SP, P and P. Right? Okay. Coming to what is pi bond? What is pi bond? Pi bond. Okay, symbolically like this. The covalent bond, which is formed by overlapping of two atomic orbitals along sideways or lateral overlap. Okay, is called pi bond. Symbolic it is given as this. And remember, in pi bond always the symmetry is only perpendicular. It is observed only. There is no SS, no SP, only P and P. For example, atoms will be like this. They should be perpendicular to each other. Okay, very best example you can give here for oxygen. Or else they should be first perpendicular to each other. That is important. Then only they will overlap like sideways overlapping. This is sideways overlapping or lateral overlapping. That's leads to what? Pi bond. First condition, they should be perpendicular, not on horizontal or along the internuclear axis. Remember, first this is to be important. Now I will tell you, for example, here formation of oxygen molecule. Okay, then we will come to know what is this pi bond actually. Consider formation of oxygen. One oxygen atom A, 1s2, 2s2, 2, 3, 4. 6 electrons are there. Okay, here see. Last one. Px, Py, Pz. 2px, 2py, 2p. Third one is there. Right? 2p4 it is only Py, Pz orbital. Of two oxygen atoms. Be like that. This is one oxygen atom, this is another oxygen atom. Px, Py, okay, Py, like this. This means this is Px and this is Py. This is Px and this is Py. In oxygen, you know, this is sigma bond. Later, they are perpendicular to each other and form what? Double bond. Oxygen and oxygen, one sigma bond and one pi bond. Above and below they will form only one. This one no. One will form only one pi bond. One sigma bond is this one and one pi bond. This is structure of oxygen. See. Okay. Generally, see, you have to imagine this. Just please here, this is Px, this is Py and this is Pz. Divided double because oxygen in P orbitals are double shaped. Therefore, this is Px, this is Py. Like this another oxygen Px, Py. Right? So like this they will overlap and will form a, that means will form one sigma and one pi bond. for oxygen, right? Okay. Then coming to nitrogen also. In nitrogen, please try to remember, nitrogen is having N triple bond N, 2 pi 1 sigma, right? So see, pH, Py, or you nothing oxygen. Another one, pH, Py, right? So this is pH, this is Py, like this pH, Py of another nitrogen, then Pz will be like this, Pz and Pz. First you see, these two will come closer to each other. Okay, it will form one sigma. This will overlap to one form, one pi. Another, this also they overlap here to form another pi bond. Below one bond. Like this, nitrogen will be having triple bond, sigma above pi. Py 1 and Pz 1, remember. Like this is very important for pi bond. Remember students, for pi bond you have to be very perfect with your atomic structure knowledge also. Px, Py, Pz. 3 dimensions you have to imagine like this. Okay? This is about pi bond. What is pi bond? The covalent bond which is formed by overlapping of 2 atomic orbitals along the sideways or lateral overlapping. That is called pi bond. Now last, just a reminder, difference between sigma bond and pi bond I will tell you. And remember here there is only one overlap, that is P and P overlap. There is no SP. And this pi bond is weaker. Why? Because extent of overlapping is less, probability is less. That's why pi bond is weaker than sigma bond. Sigma bond is stronger than pi bond. Why? Extent of overlapping of internuclear axis C is more than the sideways or lateral overlapping. That's why sigma bond is stronger than pi bond. Very, very important for theory 1 marks. They will ask you, why sigma bond is stronger than pi bond? Because extent of overlapping is higher than the sideways overlapping. That's why sigma is stronger than pi bond. Now coming to lastly, differences. Differences between sigma bond and pi bond. Let us see. Sigma bond and pi bond. First we already wrote first one, formed by how? Axial overlapping or overlapping of atomic orbitals along the internuclear axis. Formed by axial overlapping of 2 atomic orbitals. In short, 2 atomic orbitals. This one formed by sideways or lateral overlapping. Sideways overlapping of 2 atomic orbitals. Okay? 2 atomic orbitals. And here sigma bond is stronger bond. Why? Extent of overlapping is high. Okay, it is weaker bond. Third, extent of, there are SS, SP, P and P overlapping. But here only P and P by overlapping. It is present alone or with pi bond, but pi bond is always silicon bond. Remember. Okay? These are the 4 differences very important for theory purpose. For theory purpose, very important difference between sigma bond and pi bond. Another also can add extent of overlapping is more for sigma and less for this pi bond. Okay? That's why for 1 mark sigma bond is always stronger than pi bond. Why? Because see here, there are 3 types of overlapping. Here only 1 type. Here 75% probability. Here 25% probability. 75% is more than 25%. That's why higher the extent of overlapping, stronger the bond. Remember. Okay. So that's about valence bond theory and the 2 types of very important. Now you come to know orbital overlap picture of covalent bond, which will overlap in 2 fashion. One along internuclear axis or head-on overlapping. Another sideways or lateral overlapping. If it is head-on or internuclear axis, sigma bond. Sideways or lateral overlapping, pi bond. Okay, so please remember, for theory purpose, in oxygen, in double bond, 1 sigma, 1 pi. Nitrogen, remember, please remember students, 1 sigma, 2 pi. Sigma in the middle, pi on above the plane, 1 below the plane. Remember always, in alkane, sigma bond, if it is single bond, definitely sigma. If it is double bond, 1 sigma, 1 pi. If it is triple bond, remember 2 pi, 1 sigma. Alkane, alkene, alkynes. Even in hydrocarbons, alkanes always sigma. Single bond. Double bond, 1 sigma, 1 pi guarantee. And triple bond, 2 pi, 1 sigma. So this information compulsory you should know. Okay, so that's about valence bond theory and 2 types of covalent bonds, sigma and pi covalent bonds and differences. And I shown you examples, orbital overlap picture. Further in hybridization, once again I will take you very clearly and I will go very slowly. So the next class, tomorrow's class, I will go very importantly, hybridization. Remember students, hybridization. To understand this one concept of hybridization, you should have to read compulsorily this valence bond theory. Without this, we can't understand hybridization. Please, students, I am requesting you, please go through valence bond theory so that you can enjoy next tomorrow hybridization. Hybridization I will take 2 to 3 classes. It's a very, very important concept for theory as well as for CET and basic for our organic chemistry. All this chemical bonding is very important for the basic for organic chemistry. Okay? So we'll stop here. Thank you. Enjoy the day. And bye from PANCHNATH.